About in 13.3 is we're going to talk about some more statistics. And in case you don't remember, last week on Friday we talked about this normal curve thing, and it can be used for a lot of things. Statistics is the language that talks about numbers involved in any area. It could be public health, it could be politics, like right now we have the elections that are being run, and you'll see a lot of stuff with bar graphs, pie charts, percentages in the newspaper, in the media. And so all that's statistics. It works in psychology. It works in the food service. A lot of things. And so they use that as the mathematics to kind of describe what's going on. So it's kind of important to be a good consumer of information, and knowing and understanding statistics can help you do that. For example, you're going to see again today this thing that we call the normal distribution or the normal curve. And if you recall, we talked about this thing in the middle that was called our mean. And sometimes we used x bar, sometimes we use the letter mu. So the x bar stands for when we're taking a sample, and the mu is when we're talking about a whole population. Like if I said, what's the average height of a sophomore girl? And I looked at only the sophomore girls in this class, I'm using the number that's called x bar. If I look at all sophomore girls, period, that's looking at this thing called mu. In essence, we usually we'll be using the x bar no matter what the name is that they call it. Then every single jump that you make on this normal distribution is called a standard deviation. Standard deviation. In our calculator we called that SX, but they told us that we also could use sigma. So the S stands for when we're talking about a sample, the sigma is when we're talking about, or this sigma symbol is when we're talking about populations. And so I would jump one standard deviation over here, then another standard deviation, another one over here, another one over here, and I can keep on going. And what we're going to talk about today is, what does that look like when we're talking about certain things? And when we talk about these certain things, like for example, if I talked about those sophomore girls, and I told you, hey, the average height of a sophomore girl is 5 foot 5 inches. I could write that down as my mean. 5 foot 5 inches. And then if I told you the standard deviation was 2 inches, that means that the next spot on this normal distribution would be 5 foot 7 inches. And then the next one would be 5 foot 9 inches. And then the next one would be 5 foot 11 inches. And if I went the other way, I could tell you that this spot over here would be 5 foot 3 inches. And then 5 foot 1 inch. And so on and so forth. And what we're going to learn today is those are not considered normal numbers. When we talk about statistics, it's kind of confusing when you talk about a standard deviation when you have to use different numbers for every standard deviation. Like if I say I'm 1 standard deviation away, but that's 2 inches. But what if I talk about weights and the standard deviation is 7 pounds? And then what if I talk about IQ and the standard deviation is 15 points? And so all these numbers are different no matter what you're talking about. But today we're going to learn about something called a z-score, which is coming up next. And a z-score standardizes everything. So no matter whether you're talking about inches, pounds, IQs, body fat content, percent of calcium in a vitamin, anything, you can change all the scores to the same kind of thing. And that normal curve and the z-values look like this. So I draw my graph, and instead of having 50 or 5 feet 5 inches and all that, I would have a z-score of 0. I would have a standard deviation of 1. I'm 1 standard deviation away. I have 2 standard deviations away. 1 standard deviation to the left, or -1 standard deviation. 2 standard deviations to the left, or -2. So all of these scores, IQs, weight, body fat, whatever, all turns into 0, 1s, and 2s, positive and negatives, no matter what you're talking about. And that's called the normal distribution. So in order to do that, you have to know how to use a z-score, because these values are the z-values for all of those 5 foot whatever and any other number you want to talk about. The way that you find it, there's a formula. It looks like this. The z-score is equal to your value, whatever x value you have, minus your mean divided by your standard deviation. All right, so there's a rule, and I talked about this a little bit last week. If you look at this graph, this normal distribution graph, and you look inside, or in other words, maybe underneath this graph, and I look at some standard deviations, and I look like 1, 2, or 3 standard deviations in either direction. This 68, 95, 99.7% rule is saying the following. If I look in between, so here's my mean, right here, this is my x bar. And if I look one standard deviation in either direction, let's say from here to here, that this amount of space in here is 68% of the data that's out there. So if I'm talking about women's heights or sophomore heights, and I say the average sophomore is 5'5", then if I go 2 inches on either side, 68% of all sophomore women will fall within 2 inches of 5'5". That's what it's saying, because that's one standard deviation away. Now, if that's true, hopefully you understand at that point in time that means I have 34% here and 34% here, because that's 68%, right? So 68% within one standard deviation. One standard deviation. If I go out to the next standard deviation, so here's the next standard deviation right here. There's going to be 95% of your data that's within 2 standard deviations. So now if I look at this graph, not only am I talking about this stuff that's inside of here in the purple bands, but I'm also talking about the orange stuff as well. All of that. Okay, so all of the purple and all of the orange both add up to 95%. That means that inside of that stuff over here, if I need 95% and I split that in half, that's 47.5%. So this has to be 13.5 inside of here. Now you can either figure that out on your own mathematically or you can memorize it. It's up to you. If you were to add up the 13.5, the 34, the 34, and the 13.5, all of that together within 2 standard deviations is 95%. So here was 1 standard deviation, 2 standard deviations to the right, and 1, 2 to the left. And then the last part of what they're saying, of course, then means that if I'm looking at the outside part here, I'm talking about 3 standard deviations away, and that stuff and everything in between those 2 blue bars, all this stuff, totals up to 99.7% of the material. So 99.7%, why don't you go get a drink, is within 3 standard deviations of the mean. And maybe a good way to see it, if you're looking at it, is, if you're writing it down, here is 68%, here is 95%, and here is 99.7% of the material. Questions about that?
Would 2.35%?
Great question. I think it's actually 1.35 because you have 2.7 that you have to split into half. So that's 1.35. So this is 1. I should just put an arrow. So this is 95, right?
Yeah.
So from 95 to 97, there's an additional. Oh, sorry. What did I say?
You said 1.35.
Oh, my bad. So there's an additional 4.7. So 2.35 is correct. So that's 2.35, and this is 2.35, not 1.35. My bad. So good job. You have to split it in half because there's two tails. Now, confidence intervals have something to do with these z-scores and this range of information. So like, for example, if I was talking about a 68% confidence interval, that's within one standard deviation of the mean. So if I wanted a 68% confidence interval, that's this right here. If I wanted a 95% confidence interval, that's this right here, 2 standard deviations. Some of them are not so easy. You know, you have to find them in different ways. And 3 of the most popular ones that we're going to talk about are the ones that are on page 748. And so I'm going to draw a box. You don't have to write that down right this second, but I just want to tell you that on page 748, they give us a box that has these values in it. So the confidence interval and then the z value that goes along with it. So for example, up in my picture, a confidence interval of 68% has z values of 1 and -1. -1 to the left, 1 to the right. The 95% confidence interval is 2 standard deviations, so -2 and 2. But sometimes they don't really care about standard deviations. What they want to talk about is percentages. Like, what if I want 90% of the people to be in my confidence interval? What would I use then? Well, I don't know, because 90% somewhere in between 68 and 95. But that's a pretty common thing to ask. If I want to get 90% of my population, how do I do that? So what they're going to tell you is if you want 90% for your confidence interval, you're going to use the number 1.645. If you wanted 99% of the people to be included, you're going to use the z value of 2.576. And maybe the last one that you might want is if you had 99.9%. Then you're going to use a z value of 3.291. And so sometimes you talk about groupings. And when you're trying to do a survey and you're trying to reach the vast majority of people, I want 70 or 90% of you to get A's in here. Well, what are the z values? What's the likelihood that that's going to happen? What would the z values be? Or how many standard deviations, in other words, would I be away? So a z value of 2.576 means that you're 2.576 standard deviations away from the average. So that's pretty tough to do. One of the things that you find out soon